Hello and welcome to today's physics video. I went back through my files from the last couple of years and I found this from 2 years ago, which I didn't have time to get to last year due to COVID. And so I had forgotten about this PowerPoint, but I had some requests to go over this crane problem here from the challenge assignment yesterday. And as I was just looking through my materials to see what I had, to see if I had an answer key for that crane problem somewhere in my files, I found that not only did I have an answer key, but I had a whole PowerPoint that went through it step by step. So I figured, well, okay, why record a whole new video if I've already got this PowerPoint? Why don't I just turn that into a video? And as a bonus, I also have this problem from the torque practice. And that's a problem that will actually um, resemble the types of problems that we're going to see on the torque mini quiz, which I do think we'll have time to get through. And I'm going to make sure that it's um, not too stressful, fairly short, just like the last mini quiz we did before we went remote. But a problem like this one is a lot more similar to what we might see on some sort of assessment, whereas the crane problem, that's just extra credit because it's super challenging. So let's look at this one. We've got this guy, he's holding a 10 kilogram bucket, and he's got his arm, and his arm his arm has a mass of 6 kilograms, and he's holding his arm up at an angle of 30 degrees. And so because of the laws of, vertical angles and complementary angles and all of those wonderful things we love so much from geometry, his arm being at 30 degrees also means that the angles of these two forces are at 30 degrees. If you don't believe me, ask Mr. Mead. That's a joke. Don't bother Mr. Mead with stuff. If you don't believe me, I can show you. I like to make fun of folks a little bit. So the first thing we want to do here, if my screen will work correctly, is make ourselves a free body diagram, just like always. But unlike a forces free body diagram, when we're looking at a torque problem, it's not just the forces that matter, it's also the location of the forces that matters. So we can't just draw a box anymore, we've got to draw a line. This line represents our arm. With the pivot point here, that's the shoulder, that's supporting all of this torque. And then we've got the forces involved, such as the weight of the bucket, which is at an angle of 30 degrees relative to the arm, and the weight of the arm itself, which we're going to assume the arm is symmetrical. Obviously, different parts of your arm have different weights, so that's not the best assumption ever. But we don't really have a way to account for that mathematically with the information provided. So the best we can do is just kind of treat your arm like one solid object of uniform weight, and therefore we can say it's balanced in the center. To be honest, the center of mass of your arm is probably somewhere pretty close to the middle anyway, so it's not the worst approximation ever. So we're just going to go ahead and say the weight of the arm is balanced out, and so we can, through symmetry, go ahead and represent it with a force vector directly in the center of the arm. Now this looks a little weird, right? We're used to having free body diagrams where gravity is pointing straight down. Here we're looking at a free body diagram where gravity is pointing down and to the left off at some angle. And it's like, what planet are we on now where gravity isn't going straight down anymore? And that's one of the things that makes torque much more challenging. And it's not just torque. Anytime you have some strange angular situation like this, you can do a technique that's called rotating the axes, which is what we've done. We've already done rotating the axes. That's how we got from here, where the arm is pointing up and to the right, and perpendicular is pointing up and to the left. took that and we rotated it downwards by 30 degrees. When we did that, now our arm is pointing straight off to the right, and perpendicular is going straight up and down. So we haven't changed anything at all. It's like you took your piece of paper and you turned it 30 degrees clockwise, and now you're looking at it from a slightly different perspective. So that's all we've done. We haven't changed the situation at all. We're just now looking at it from a position where the arm is flat rather than angled, because it's a little easier to work with that way. So that's something called rotating the axes, where you take something that's angled, and it's basically just like turning your piece of paper until everything's left, right, and up and down. Let me clear off some of this extra stuff here. So we know that the distance of the bucket is 80 centimeters or 0.8 meters. And we know that the weight of the arm is, we're going to assume it's centered right in the middle of the 80 centimeter arm, which would be 40 centimeters or 0.4 meters. And I do apologize if my bird is yelling through two doors and over the video. Like I said earlier, my bird really likes torque. I don't know why. So sorry if she's too loud, but I don't think she's too loud. So here's where we left off on the last slide. We've got our free body diagram. So now let's balance it, right? So what is our net torque? Our net torque is these two torques added together because they're both going counterclockwise. So let's go ahead and say, they're not going counterclockwise. Getting my directions mixed up. They're going clockwise. We got that. So we're going to go ahead and say clockwise is positive, and therefore we've got two positive torques that the shoulder must support in order to stay lifted. So now we use our torque formula, right? Torque equals force times radius times the sine of the angle between them. Apparently, 2 years ago when I did this PowerPoint, I really liked putting the sine of the angle in the middle of the equation for whatever reason, but multiplication is commutative, so that doesn't matter. And now we just need to fill in the information. So really the challenging part of this problem is setting up the information, setting up your diagram correctly. Once you get to this point, it's just some multiplication in a calculator. So what's the force of the arm itself, the weight of the arm? It's mass times gravity. So 6 kilogram arm, 9.8 gravity, 58.8 newtons of weight on the arm itself. And the bucket weighs 98 newtons because the bucket's 10 kilograms. So 10 times 9.8 gives us 98. Sine of 30 is one of my favorites because it's a nice even 0.5. 30 degrees is a really easy to use angle. So plug that information in, punch it in the calculator, solve. 50.96 Newton meters worth of torque that the shoulder must support. So technically, if you want, you can look at this two ways, right? Because in a situation where someone's lifting something with their arm, as long as they're continuing to lift it, the net torque is quote unquote zero, but that's because the muscles within the shoulder itself are applying a resisting torque to hold everything up. But in this case, if you think of it as how much torque is on the shoulder, how much torque does the shoulder have to support? Well, these two forces are trying to drag the shoulder down in the clockwise direction with a 50.96 Newton meter worth of torque. So the shoulder muscles will have to resist that with 50.96 Newton meters worth of torque in the counterclockwise direction, or else the arm will fall. So that's what we just solved for here, is how much torque does the shoulder have to withstand in order to stay lifted. So here we are on this one. Very challenging problem. This is likely the hardest problem on the hardest worksheet. I'm going to say it's more challenging than even the dragging a box problem was. Dragging the box problem is the hardest problem of the year that's not extra credit. This is the hardest problem of the year, including extra credit. The very first time I assigned this worksheet, it wasn't extra credit. That was mean of me. I apologize to those students. Most of them have graduated by now. I learned my lesson. That was cruel. Now since then I'm like, this question needs to be extra credit. So thank you to those of you who took on the challenge to try and do the torque challenge bonus problems. That was a very challenging worksheet, and just attempting it is worth some extra credit. So, however, if you're not interested in challenging yourself with that higher level torque stuff, if you're like, I got what I need for the quiz, I'm going to go work on something else now, then that's just fine. You can go ahead and exit the video and have a great weekend. But for those of you who wanted to see this problem in action, you're going to get a lot of great skills here that if you go into any sort of physics or engineering major, these skills are going to be very useful in those areas. So, as always, we're going to start with the free body diagram, but this time the pivot point is not on the edge, it's in the middle. And in fact, that's what makes this such a pain in the butt. So, what forces are involved? Well, we have the two obvious ones, the object itself, which we call the load. We have the weight of the counterbalance over on the left side here, which I'm going to call FW for weight, counterweight. And then the weight of the left side of the arm, trying to pull it down in the counterclockwise direction, and the weight of the right side of the arm, trying to resist that going the other way in the clockwise direction. So, if we were looking just strictly forces, right, we'd see, oh, 4 forces in the negative y direction. However, now we need to train our brain to think in circles rather than xy. So when we think in circles here, we see 2 forces going one way and 2 forces going the other way, right? We've got 2 forces on the right side going clockwise. That's a pretty bad arrow. And 2 forces on the left trying to go counterclockwise. So even though all 4 forces are going down, they're still going in different directions when we're thinking in torque, because torque is a circular thought process. So it wants us to figure out where to put the pivot point. That is the challenge here. So this is where some algebra skills come in. We might have written a let statement here. In fact, I'm going to do that just to call on our Algebra 2 skills here. I'm going to say let statements are really an Algebra 1 skill, just so you know. Let x equal length of left side. So from the pivot point to the edge of the left side here, that distance we're going to call x. So then, what's on the other side here? Sorry, before we get to the other side, if the arm is x meters long, then the weight, again assuming symmetry, is going to be centered halfway to that, which would be half of x, or x divided by 2. So the distance for our gravity force on the left side is x divided by 2. The counterweight being all the way on the left side gets the full x. So what would be left over on the other side? Well, the rod is 56 meters long, right? So the whole thing is 56 meters. So if the left side has x of those meters, then the right side has whatever is left over, 56 minus x. And then the weight on the right side The weight on the right side is half of that, right? So take 56 minus x and divide it by 2. So 56 divided by 2 is 28. X divided by 2 is x divided by 2. So halfway. So we've got all of our distances now in terms of x, which is eventually we're going to have an equation to solve for x. So we've got our distances. We need to get our forces. Now, the force of the counterbalance and the force of the load are going to be pretty straightforward because we have those masses. We know the counterbalance is 2,500 kilograms. So take that times 9.8, and we've got force of the counterbalance, force of the counterweight. We know the load is 860 kilograms. So again, take that times 9.8. We've got the force of the load. What we do not know at this time is how much mass is on the left and how much mass is on the right in terms of the crane itself. We know the entire crane is 750 kilograms, but we don't know how much of that is left and how much of that is right. And that's where this problem gets exceptionally tricky. It's been pretty tricky so far. This is the real tough step where you've really got to think it in terms of logic. And again, making that assumption that the weight is evenly spread out throughout the crane. So the left side isn't made of heavier material than the right side or anything like that. It's a symmetrical, even crane. With that assumption, we can actually get some information on the masses of the two sides without knowing yet the distance. And I'm going to show you how. So again, we've got our distances in terms of x. We've got our forces in terms of nothing because we don't know them yet. So if we can somehow get everything in terms of x, right, everything as a function of x, then we can solve for it because we'll have one equation, and that's all we need to solve for one variable. In this case, that variable would be x. So we just need to find a way to get these forces in terms of x, and then we can solve. So I'm going to go ahead and call clockwise here positive. In the end, it's not going to make a huge difference which way we call positive or negative, but I still like to, it's always a good idea to set one direction as positive. What does that mean? It means the right side forces are going to create positive torque, and the left side forces are going to create negative torque because they are going to try and spin the thing counterclockwise. So assuming all is well, the net torque is 0, right? Because the crane hopefully is not falling over. So that means we have balance. Therefore, the clockwise and counterclockwise forces are balancing out. They're even to each other. So we've got our positive forces of the load and the weight on the right side, our negative forces of the weight of the left side and the counterweight, and those are balanced out for a total of 0. Whoops, my animations are a little out of order there. That's the second time that's happened this week. Sorry about that. But anyway, you can see we go ahead and move those left side forces on over to the other side of the equation, and we get that our right side forces, torque, I keep saying forces, I need to say torque. Our right side torques equal our left side torques. So now let's use our torque formula to figure out what those x's might be. And one thing that's nice about this problem, pretty much the only thing that's nice about this problem, is that all 4 of these forces are already at a perfectly 90 degrees perpendicular angle. So we don't need to worry about any signs. We can just do force times radius, or force times distance if you want to think of it that way. So we've got the force of the load over here on the right. Force of the load times the distance of the load, which we learned earlier was 56 minus x. Then we've got here force of the right side, the weight of the right side of the crane times that distance. And then same thing on the left. The weight on the left times the distance, which was x divided by 2. and then finally the counterweight's force times its distance, which is the full x. So we know the mass of the load and the mass of the counterweight. We do not know the mass of the left side of the crane or the mass of the right side of the crane. We just know that together they have a total mass of 750. But we can, if we think about it logically, we can get that mass as a function of x. We can get the mass of the left side and the mass of the right side as a function of x that uses a fraction to distribute that weight between the left side and the right side. So the next slide here is going to show us how that's done. So again, total length on our crane here is 56 meters. X of those meters on the left. So as a fraction or percentage of the total crane is 56 meters. X of those meters are on the left. There's X divided by 56%, if you want to think of it that way, of the crane is on the left side, and the rest of the crane is on the right side. So how much mass is on the left side? Well, the left side portion of the crane is X divided by 56. So that means that the mass of the crane is going to be X divided by 56% of the full 750. So the whole crane itself is 56. The left side has X of that. So that tells us what fraction of the crane is the left side. Then we multiply that by 750 to figure out what fraction of that 750 kilograms is on the left side. So again, it's more of a logic problem than anything, and that's where the real challenge comes in. This is not something you can just get an equation for. You just kind of have to think your way through it, and hopefully it's making sense. So if this is making perfect sense to you, then you'll be an excellent engineer if that's what you want to do. So, it's a great sign if that's where you're headed with your career. So what's the mass of the right side? Well, everything else, right? So we've got 750 total. This much of it is on the left. So everything else is on the right, right? So this right here is the left side, right? So we take the full 750, we subtract out what's on the left, everything else is on the right. So that's what we did here. We took 750 minus what's on the left, and that gives us what's on the right. And then over here, I just simplified it a little bit by factoring out a 750 from that equation. So now we have an equation for the left side's mass in terms of x, and an equation for the right side's mass in terms of x. And now we can solve for x, because x is our only variable left. The only thing left that we don't know is x. We know force of the counterweight, because it's just mass times gravity here, right? Mass times gravity. We know force of the load, because it's just the load's mass times gravity. We know the force of the left side, because it's just the left side's mass times gravity, and same thing for the right side. So we know everything except for x. X is the only thing we don't know. So now let's use our torque equation from our last slide here in order to solve for x. So again, there's that equation that we got from 2 slides ago. And at this point, we were like, well, we're stuck. We can't get force gravity right or force gravity left, so we're stuck. And that's when we went and found out how to get force gravity left and force gravity right. So now it's time to plug it all in. So it's going to get very messy. Just be warned. That's one of the things that makes this problem difficult, is there are numbers and x's and it just gets messy. So be forewarned. There you go. So force load is mass load times gravity. Force gravity on the right side is mass right times gravity. Force gravity on the left side is mass left times gravity. And force of weight, force of the counterbalance, the counterweight, is mass of the weight times gravity. So now let's plug those masses in. Yes, very ugly. I warned you. So the load mass is 860. The mass of the right side was that 750 times 1 minus x over 56. The mass of the left side was the 750 times x over 56. And if you need to rewind the video a little bit to go back to the previous slide where we calculated those masses, you can see where those numbers are coming from. And then the mass of the counterweight is 2,500. So everything here is in terms of x. We have one equation. X is the only thing we don't know. Now, granted, there's like 8 of them. I think there's 6. Granted, there's 6 x's in there, so it's going to be a pain in the butt to solve, which is where I introduce you to Wolfram Alpha. So wolframalpha.com, I call it the Google of math. You punch in any sort of crazy math problem, linear algebra, calculus, it doesn't matter. It can solve it for you, and it even tells you how to do it step by step, and it gives you graphs, it gives you different forms. It's like your math best friend. Don't use it on the final. Probably should have maybe not taught you this now, but you know what? Whatever, I'm doing it. So don't use Wolfram Alpha on the final, please. That's a little bit too much information. Your calculator is good enough, but I can't make it this easy on you, because watch how great Wolfram Alpha is here. Oops. Well, a little sneak preview of the answer there. My bad. But anyway, here's Wolfram Alpha. We punch in our equation and we press go. And here's what you would see. You'd see your equation here, so that you can double check and make sure all of your parentheses are correct. So that's one thing I really like, is it takes your keyboard from the equation here and shows it to you in a little bit more normal of a way, so you can double check and make sure everything looks correct. It simplifies the math for you. It graphs it for you, so you can do solve by graphing. It gives you alternate forms, so it rearranges things for you. I honestly don't even remember what expanded form means. Oh, it just means that all of the parentheses get multiplied together. It gives you the answer on a number line. And then finally, kind of hidden underneath all of this awesome math stuff, is the answer itself. It solves for x. So you punch an equation into the search bar with x's in it, and it recognizes that, and it goes, hey, that's an equation, and it solves for x. And you can see that x is about 16.8. So what does that mean? It means that the pivot is 16.8 meters away from the left side. Right? So now we go back here. Here's where we left off. And x is 16.8 meters away from the left side, right? So if we look at our crane up here, here's our crane. It means that our pivot point here, our support beams are 16.8 meters away from the left side, leaving the right side here, if my pen would work, with whatever 56 minus 16.8 is, which is 39.2 meters. So, ugly problem, right? Lots of math, lots of assumptions, lots of logic, lots of information you just kind of had to figure out without being told. We were given very minimal information on this problem. And a very, very challenging task. and we had to use a lot of logic and reasoning in order to construct equations that eventually got to the point where we have one equation with one variable that we can solve. And if we wanted to, honestly, we could have, we have the skills to solve this equation here by hand. It would probably take about an hour to an hour and a half to do. But we could multiply things together and then subtract and then multiply again and subtract and rearrange and try to get x by itself. It's not impossible, but the computer can do it in about 2 seconds. So why spend 2 hours doing it ourselves? So if you go into any sort of engineering or physics field, um, even chemistry probably, Wolfram Alpha, you're going to love it. It's going to save you so much time. So that's it for this crane problem. I hope this video is what you guys were looking for. I hope it wasn't too long, and I hope you found this challenge enjoyable. So let me know if you guys have any questions, and have an awesome weekend.